Okay, so today's lesson is on finding rational zeros. So the first thing we're going to talk about is the rational zero theorem. And this theorem basically is there to tell you if you had to pick out some zeros to start with to find the other zeros. Right now, if I don't give you anything to start with, you're starting really with an infinite amount of numbers. So this theorem is going to help you narrow down your choices so that if you are going to try to find the zeros, you have a starting place. So if f of x is a polynomial with integral coefficients, then each rational zero of the function is of this form. P over Q, which represents the factors of the constant term over the factors of the leading coefficient. So for example, if we needed to find all the possible rational zeros of this function here, we're going to first look at this constant value here, which is 32. And that would be our P, let's say. And then we'll look at all of our coefficients of this coefficient over here. We'll look at all the factors of that coefficient there. And this you would say is your Q, right? So first thing I'm going to do is write down my factors. So the factors of my constant term would be 1 and 32, 2 and 16, because 2 you can divide into 32 evenly. 3 does not go into 32 evenly. 4 does. 5, 6, 7 do not, and then we're back to 8. So these are all of our factors of that constant term there at the end. Now the Q, which is this leading coefficient here, is just going to have the one factor of 1 since it's just a 1. So then we're just going to set up the possible factors in a list. Okay, so our list of possible rational zeros is going to be positive and negative 1, positive and negative 2, positive and negative 4. I'm just putting them in order. Positive and negative 8, positive and negative 16, and positive and negative 32. Now, sometimes they can also be written with 1 plus minus out in the front and then some sort of a grouping symbol. Then you can list all your numbers inside of the grouping symbols and just put the plus minus once on the outside. And that would signify that all of those numbers are going to be both positive and negative. So really, even though we have 1, 2, 3, 4, 5, 6 different numbers here, we really have 12 possible choices, right? Or 12 possible rational zeros. So what that would mean is those are the 12 possible numbers that could be x-intercepts that are either integers or whole numbers or fractions, because those would all be considered rational, or some kind of a number that could be written as a fraction. Now, of course, this does not account for imaginary solutions. So if there's any imaginary solutions, this will not account for those. It will also not account for any irrational numbers. So if you had any of those like long decimals that don't end and they don't have any specific repeating pattern to them, those are irrational numbers as well. So we commonly see those with radicals, like if you had radical 5 or radical 2 or something like that. And then, of course, this would not include imaginary numbers either. Okay, so now that one wasn't too bad because our coefficient of our lead term was a 1, but in this next problem, we're going to look at one that has a number other than 1. So my p-value is just this 10 here, and then I'm going to be focusing on this 6 for my q's, okay? So my factors of my 10 would be 1 and 10 and 2 and 5. The factors of my lead coefficient, or this q value, would be 1 and 6 and 2 and 3. So now it gets a little bit trickier when we go to do this list, because first we have to take each of our factors of this constant, so all of these p-values, and we have to write them all down: plus minus 1, plus minus 2, plus minus 5, plus minus 10. Now those first 4, or really 8, were all of my p-values over this factor of 1, because if they're all over 1, then we're just going to simplify them all to the whole numbers or integers that they are. Well, then we have to repeat these again, these 4, but this time we're going to put them all over this 2. So we have plus or minus 1 over 2, plus or minus 2 over 2, plus or minus 5 over 2, and plus or minus 10 over 2. Now continuing on, we're going to do the same 4 factors for my 10, those 4 p-values, but this time they're all going to go over this factor of 3. So I have plus or minus 1 over 3, plus or minus 2 over 3, plus or minus 5 over 3, plus or minus 10 over 3. And now from there, we're going to do this one more time, and this time we're going to use this 6 as our denominator. So plus or minus 1 over 6, plus or minus 2 over 6, plus or minus 5 over 6, and plus or minus 10 over 6. Now, before we finalize this list, we want to double check because we know those first 4 were all whole numbers or integers, so they can't be simplified any further. But some of these fractions could probably be simplified or reduced, and then that will actually, we'll notice that they're a repeat of something we've already listed. So for instance, 1/2, there isn't any fractions prior to 1/2, so that's the first time we're seeing that, so that's fine. But then we have 2 over 2 as our next term here. But 2 over 2 simplifies to just 1, which we already have in our list. So this one is going to get eliminated because we don't want to be redundant and list the same number twice. 5 over 2, that simplifies to 2.5, which is not previously on our list, so we're going to keep that one. 10 over 2 can simplify to 5, which we already have on our list, so we're going to get rid of that one. Now the next set of numbers are all over 3, which we don't have any fractions over 3, and none of these can be simplified or reduced, so we're going to leave all of those. 1/6, same thing, is already simplified, and we haven't seen that number yet. 2/6, however, can be reduced or simplified to 1/3, which we already have in our list. 5/6 is already fully simplified, and it's not a repeat, so we're going to keep it, but 10 over 6 reduces to 5/3, which we already have in our list. So then in that situation, these 4 that I've crossed out would not be included in our final list. We would just include all of the other ones that have not been crossed out. So there's actually 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24 possible rational zeros for that particular polynomial. Okay, so the whole point of finding these is so that if you needed to find your zeros or your solutions, in the last section, I gave you one to start with. I said, find, if x equals 4 is a 0, find the other zeros or whatever ones were left. So you had a starting place, and then you could factor to find the remaining ones, and it wasn't too bad. But this time, we have to find all of them, and you're not given a number to start with. So first of all, just to remind our fundamental theorem here, is that our lead term, which is the term with the highest degree, is going to basically tell us how many zeros or solutions that we're going to have. So for this particular problem, it's a cubic polynomial, so that x cubed tells us that we're looking for 3 solutions. So I'm just going to go ahead and write that there so I know what I'm looking for. Now, it's not giving us something to start with, so then I'm going to have to create my little list so that I'm not randomly picking numbers out of thin air. Now, in this particular case, I'm going to be using this 12, and I'm going to be looking at all the factors of 12. Of course, are 1 and 2, 2 and 6, 3 and 4. I would also have to look at my factors for this lead term, but it's just a 1, so all of these numbers here that are factors of 12 are just all going to go over 1. So my list is simply positive or negative, 1, 2, 3, 4, 6, and 12. And remember, each one of those is both a positive and a negative, so there's actually 12 different choices that we can start with. So at this point, you would just want to pick a number from that list. It is still a little bit random, but that's better than starting with, a whole bunch of numbers. And what you're going to do is you're going to synthetically divide out a number until you get a remainder of 0, because when you get a remainder of 0, that tells you it is one of the zeros or solutions of the polynomial function. So I'm going to carry down my coefficients like we would do for synthetic division or synthetic substitution. And then I'm going to ask you at this point to just pick a number from that list. So I don't know, I guess I'm just going to try 2. So if I try a 2, for example, I carry down my 1. 1 times 2 is 2. I'm going to add those up. I get 4. 4 times 2 is 8. Add those up. I have -3. -3 times 2 is -6. But that gives me a -18. So I know that that won't work, and that is not one of the answers. So you can either start over somewhere else or erase it if you used pencil, whatever. And now I'm going to try a different number. So maybe this time I'm going to try 3. And you can also try negatives of these numbers as well. So let's see what happens here. So I drop down the 1. 1 times 3 is 3. Add those up, I get 5. 5 times 3 is 15. Add those up, I get 4. 4 times 3 is 12. And those give me that remainder of 0. So I know that x equals 3 is one of my 3 solutions. Now, once you get down to the point where you only have 2 left that you need to find, at this point, you can just do what we did in the last section and factor out this remaining trinomial. And you should be able to get the last 2 quite easily, so you don't have to keep guessing and checking for the remaining numbers. So once you get 1 to work, factor this equation that's left when you divide out that first number. So the 2 numbers that multiply to get 4 and add to get 5 would be 4 and 1. And then if we solve those factors using zero product property, we would get x equals -4 and x equals -1, and those would be our remaining 2 solutions. All right, so we're just going to practice this now for a few more problems. Okay, so basically here again, looking at this term, I see that this is a cubic polynomial. So right away, I like to kind of just prepare myself to know that I'm going to need 3 solutions or 3 zeros. Now, in this case, this coefficient is a 1, so that's good. So all I have to do is find my factors of 30 to make my list, because they're all just going to go over 1. So plus or minus, and my factors of 30 are 1 and 30. 30 divided by 2 is 15. 30 divided by 3 is 10. 30 divided by 4 does not work. 30 divided by 5 is 6. And then the next number is 6, which I already got, so I know I'm done. So it's plus or minus 1, 2, 3, 5, 6, 10, 15, and 30. So there's actually 8 numbers, which means that there's really 16 possible rational zeros. And hopefully one of those is one of these solutions over here. So now we're going to write our synthetic division grid out. So +1, -4, -11, and +30. And we're just going to attempt to divide out one of these numbers. So let's say I try 4. Actually, I'm going to do -4 just to try negative. Okay, so I bring down my 1. 1 times -4 is -4. Add those up, -8. Multiply those, I get +32. Subtract the 11, 21. 21 times -4 is -84, and that is definitely not going to give me a 0. So I'm just going to simply erase that. And I'm going to try a different number. So instead of -4, I don't know, maybe I'm going to try 5 this time. Bring down the 1. 1 times 5 is 5. Add those up. 5 times 1 is 5. -11 and 5 is -6. And 5 times -6 is -30, which gives me that remainder of 0 that I needed. So I know one of my 3 zeros here is 5. So now that I know that that's 5, this remaining answer here is x squared plus x minus 6. So I have an option. I could continue to try to divide off of those answers and try to pick from this list, or I could simply just factor this quadratic trinomial, which would easily factor into x plus 3x minus 2, because the two numbers that multiply to get 6 and subtract to get 1, which is what we have in the middle, are 3 minus 2. So that means my remaining two zeros here would be -3 and +2. Okay, so now we are going to do the next one. Again, we have a nice cubic polynomial here, which means we are going to have 3 answers, but we only have to worry about the factors of 9 for our list because the lead coefficient is just a 1. So my list is positive or negative, and my factors of 9 are 1, 3, and 9. So I only have 6 numbers to choose from this time, so that's kind of nice. And I have 3 solutions here. So I have a 50% chance this time of getting it to work. So doing my synthetic division, I have a 1, a -1, a -9, and a +9. And I'm going to go ahead and pick 3. I'm going to try 3 for my first one. So bringing down the 1 times 3, adding those up, 3 times 2, adding those up, 3 times -3, and I got a remainder of 0 my first try that time. So I know one of my solutions is a 3. So now for the remaining, I'm going to have this written out. So this is 1x squared plus 2x minus 3. Remember, this is your remainder, this is your constant, your x and your x squared. That's how it works. So I can factor that trinomial into x, and the two numbers that multiply to get 3 and subtract to get 2 are +3 and -1. And of course, then I can solve each of those using zero product property to get those two zeros or solutions, and it would be -3 and +1. Now, even if you started with a different number, like let's say you had started with 1, then you would still have been able to work this out. You would have just ended up factoring it a little bit differently and getting the remaining 2 solutions. Okay, so let's take a look at number 4. Again, a nice cubic polynomial with a lead coefficient of 1, so we don't have to worry about any factors there. And then we just have to do our factors of 28. So my list is, again, will be very simple. It's just positive or negative. My factors of 28 are 1, 2, 4, 7, 14, and 28. And of course, I'm going to have 3 solutions since it's x cubed. So I'm getting ready for those 3 solutions. So now I just want to try out something here. So I'm going to put in my coefficients. And I'm going to go ahead and try 7. So I'm bringing down the 1. 1 times 7 is 7. Adding those up. 7 times 14. Now this is going to be, I think it's 98, 94. And now we know that that's not going to work out because it's going to be a very large number, way bigger than 28. So I'm just going to switch this to -7 and see how that works. So bringing down the 1, -7, 0, 0, -4, and this one works out. Remainder of 0. Now notice here, this is my constant, this is my x, this is my x squared, right? So I have 1x squared plus 0x, so I don't need to write it, minus 4 equals 0. Now if I go to factor that, this is a difference of 2 squares binomial. So x, and then it would be +2 and -2. So my original solution, or my first one that I got, was -7, and then I got +2 and -2 for my other 2 solutions. Okay, so now let's take a look at number 5. So number 5, this time we have a quartic polynomial, but again, that lead term is a 1, so our list won't be too bad to make because we only have to worry about the factors of 18. We don't have to put them over anything other than the 1. So my factors of 18 are 1, 2, 3, 6, 9, and 18. And this time, of course, we're going to have 4 solutions. So we're going to be looking for an extra number this time. Okay, so when that happens, we start out the problem the same. We still want to start it out with our synthetic division. I'm not missing any terms, so I don't have to worry about putting any of the 0 placeholders. Okay, so I'm going to guess my number to put out front here. And I don't know, I really don't have a rhyme or reason or a trick on how to pick which number or anything like that. But I see a lot of numbers that are divisible by 3. I don't know if that has anything to do with it. So I'm just going to pick a 3 and see what happens. So I carry down my 1. 1 times 3 is 3. Add those up. 3 times 6 is 18. Add those up. 3 times 11 is 33. Add those up. 3 times 6 is 18. So I kind of got lucky. So I know one of my answers is 3. Now, the previous few problems, we only had 2 x's left, or an x squared. So at that point, it was pretty easy to just factor and solve. But this would be x cubic, because remember, this is your constant x squared, x cubed. So you'd still have kind of a bigger polynomial to try to factor. So at this point, I would try to find another solution from my list. So, and then let's try to divide out, one more number just to make that a little bit more factor friendly. So let's see, what do we want to use this time? Well, since I already did these problems, I know what the solutions are. I'm going to just pick number -1. Okay. If you pick something that doesn't give you the 0 at the end, then you know you have to try it over. Okay, so bringing down this 1 times -1 is -1. Adding those up, multiplying, adding those up, multiplying, and there's that 0 that I was looking for. So I know -1 is also one of my zeros or solutions. So now to find my remaining 2, you can factor. So this is x squared plus 5x plus 6. This is a factorable quadratic trinomial because I can split up my x squared. And then the two numbers that multiply to 6 that add to get 5 are +3 and +2, which would make my remaining 2 solutions -3 and -2. So those were my 4 solutions for this one: +3, -1, -3, and -2. Okay, and then we're going to do one more this time, taking it an extra degree up to x to the 5th. Now this one's kind of interesting because, first of all, when you look at the list, you're going to notice that the only factors of 2 are 1 and 2. So you really only have 4 numbers here to choose from. You have +1 and -1, +2 and -2. But because it's an x to the 5th, we're expecting to have 5 solutions. So that's kind of interesting because you only have 4 possible rational zeros to choose from. So what does that mean? Well, one, it could mean you definitely have imaginary solutions in there, and that could be making up for those ones that are not accounted for in the list. It could mean that you have irrational solutions like square root of 5 or something like that. It could also mean that, remember when we do graphs, if the parabola or the curve or whatever comes and touches that x-axis in one point, and then it goes back up in the other direction, or it comes up, hits the x-axis, and goes back down, that point where it touches the x-axis and then kind of deflects counts as a double. So it's possible one of our intercepts is one of those kinds of situations, so that number might count twice. So there's a couple scenarios as to why there could be less numbers in the list than X solutions that we're looking for. So, start out. Good news is we only have 4 numbers to try out here, so it can't take us long to find them, and we're bound to have at least a couple of these work. So +1, -1, -2, -1, +1, +2. So let's try a number. Let's just pick, I guess, 1, because 1's a nice, easy number, right? So we carry down the first one. 1 times 1 is 1. Add those up. 0 times 1 is 0. Add those up. Then -2, add those up. -3, add those up. And then we get the 0 at the end. So we know positive 1 is one of our solutions. Let's try another number. So this time I'll do 2 because positive numbers are easy to work with. So I'm going to do 2 this time. Bring down the 1. 1 times 2. Add those up. 2 times 2 is 4. Add those up. 2 times 2 is 4 again. Add those up. 2, and then I get another 0. So I know 2 was also a solution. So now I can try either -1 or -2. Well, -1's probably a little bit easier because 1's easier than 2 usually, right? So I'm going to do -1. So carrying down that 1. 1 times -1 is -1. Adding those up. Adding those up. And I get a 0 at the end again. So we know -1 is also a solution. Now at the end here, since once you get to 2 solutions left, then it's just easiest to factor. So remember, this is your constant, this is your x, this is your x squared. So we have 1x squared plus x plus 1 equals 0, and we would want to factor this. However, are there 2 numbers that multiply to get 1 and add up to get 1? There's not, so this is not factorable, unfortunately. So instead, that tells us that these 2 are either imaginary or irrational. So when that happens, you're going to have to actually solve this quadratic equation here, and we're going to do that some other way. Now, the easiest way to probably do that is to use your quadratic formula. You could also do completing the square, but if the middle number is odd, I usually don't like to do that because you get a fraction. So all the numbers A, B, and C here are all 1, so that makes it kind of easy to plug in. So I have -1 plus or minus, then this is going to be 1 squared minus 4 times 1 times 1 all over 2 times 1. So -1 plus or minus 1 minus 4, which is -3 as your discriminant, and that's over 2. Now remember when we did quadratic formula, that plus minus means you're really getting 2 answers here. So you're going to have -1 plus the square root of -3, which is really I radical 3, and that's over 2. And then you have your other answer here, which is -1 minus I radical 3 over 2. So those would be your remaining 2 answers there. Okay. All right, so now moving on to the next page, now we're specifically going to talk about x-intercepts. Now, obviously, all of your rational zeros would be x-intercepts because they're real numbers, so they're viewable on the graph. Imaginary numbers, however, are not x-intercepts. So at this point, we're really just looking for the real zeros. So if they're imaginary, we're not concerned about those at this point. If they're irrational, though, they should still be found, okay, because they're still x-intercepts. So what we're going to do now is we're going to use our calculators to kind of help us out. We're still going to work on that list for some extra practice because a lot of these numbers now have this extra coefficient in the front, so it's kind of good to practice making the list with those numbers. So first I have my factors of 4, right, which I'm just going to list those first. So positive or -1, 2, and 4. Now the factors of 2, right, are just 1 and 2. So when we listed all those whole number factors of 4, those were really already over the 1. So now I'm just going to relist those numbers over 2. So 1 over 2, 2 over 2, and 4 over 2. However, we know that 2 over 2 and 4 over 2 both reduce to 1 and 2, which are already in our list. So we're just going to not include those in our list. Now again, this is a cubic, so we know we're going to have 3 x 3 solutions or 3 zeros, and we're going to look on the graph to see if they're all x-intercepts. And that also helps you because you don't have to randomly guess from this list now, because the calculator will definitively show you which of these possible rational zeros are actually going to be x-intercepts. So you're going to go to your graphing calculator, go to your y equals 2x to the third power plus 4x to the second, or squared, minus 2x, and then minus 4. Now, when we graph it, we should visibly see, okay, all 3 of them showed up. So we see that it's crossing through at -2, -1, and +1. So we know -2, -1, and positive. Now, since we knew we were only going to have 3 solutions here, and we already found all 3 in the calculator, we know we're done. There's no more work for us to do here. Now, one little thing I want to point out as far as finding a list, the reason why it's still valuable to find this list is because you know the largest one of these numbers is likely to be as 4, and the smallest would be 1/2. So if you don't see all of the numbers on your graph, let's say you only saw 1 intercept here, but you see all the numbers that we have in our list on the x-axis, then you can be sure that the graph is showing you everything that you need to see. Because what if the x-intercept is just not on the graph, and that's why you're not seeing it? And that's why it's important to know what the list consists of. Okay, so let's go on to number 2, and then you'll kind of see what I mean a little bit more. So for this one, again, we have our lead term here, and we have the constant term, which will be factored. Now, again, this is a cubic polynomial, so right away I know I'm going to be looking for 3 x values, or 3 solutions, or hopefully 3 x-intercepts, unless some of them are imaginary. I'm going to do my list this time. I'm going to do positive or negative, and I'm going to do my factors of 25. So 1, 5, and 25. And since 2 has both the factor 1 and 2, I already did the factor of 1 on the bottom. That's why those are all whole numbers. But now I'm going to do 1 over 2, 5 over 2, and 25 over 2. Now this is really 1/2, 2.5, and 12.5. So now you can see what I'm talking about. If you went to your graph, 12.5 is somewhere off the graph that's in front of us. So if it was crossing through there, you wouldn't know just by looking at the graph. So you might have to go to your table of values or adjust your window. So let's see what happens when we type this in our calculator. We may get lucky and see all 3, and then we don't have to worry about that. So we go to our y equals, clear out the one that was in there, 2x to the third power plus x squared minus 50x minus 25, and then we hit graph. Okay, now luckily this is a cubic polynomial. I'm only expecting a maximum of 3 answers here, and I can see all 3 of them visually on my graph. I can see it's clearly crossing through at the -5 and the +5, and then it's somewhere in between the 0 and the -1, but based off of my list, I would know that that has to be -1/2. So I have -1/2, and then the positive, and the -5. And again, since I found all 3 of them in one shot, then I'm done. I don't have to do any more work to find any more solutions. Okay, so we got 2 more of these, I believe. Okay, same concept here. The factors of 18 over the factors of 3. So if I'm making my list, since 3 has 2 factors, 1 and 3, I'm going to put all my factors of 18 over 1 first. And then I'm going to put them over 3. Now when I do that, 1 over 3, 2 over 3, those are simplified fractions. But then when I would go to 3 over 3, that's really a 1. Then I would do 6 over 3, but that simplifies to 2. Then I would do 9 over 3, which simplifies to 3, and 18 over 3 simplifies to 9. So that's where I'm going to stop, because the last 4 would all reduce into something I already have. Now again, this is a cubic, so I'm expecting 3 solutions and hopefully 3 x-intercepts. So now I'm going to use my graphing calculator to see how many of them show up on my graph. So 3x squared, or sorry, x cubed, plus 12x squared, plus 3x, minus 18. Okay, so I can see it crossing through in 3 spots very clearly, -3, -2, and +1. -3, -2, +1, which were all numbers in my list. Okay, and then one more of these problems. Now this time we have an x to the 4th. So we are going to need 4 solutions for this one. Hopefully all 4 will be visible as x-intercepts on our graph. Our list will consist of the factors of 5, which are positive, -1, and positive, -5. But they're not only going to be over 1, but they're also going to be written over 2. So it'll be 1/2 and then also 5 halves. And of course, there's 8 possible there because each one of those has both a positive and a negative option. All right, so now we're going to put this into the calculator and see how many of these we can find. So there's 4 total, so hopefully we'll at least get 1, right? So we have 2x to the 4th plus 3x to the 3rd minus 3x to the 2nd plus 3x minus 5. Graph that. Okay, so now this situation, you only see it crossing through in 2 places. It looks like it's +1 and -2.5. So +1 and -2.5 or -5 over 2, right? Now, I'm pretty sure that none of these other 2 x-intercepts are not off our graph because all of the rational possible zeros here were all within 0 and 10. There was no numbers that were like really large that would be off the graph or really small. So that tells me most likely the other 2 solutions are imaginary here, and that's why I'm not seeing them. So in order to find those, you're going to do your synthetic division. And just like we did on the other problem earlier, we're just going to divide out the 2 solutions that we do know, and then we're going to see if we can solve what's remaining to find the remaining 2. Okay, so because we have 2 options here, 1 and -5 over 2, obviously I'm going to start with 1 because that's a much simpler number to start with. So I bring down my 2, multiply, add those up, multiply, add those up, multiply, add those up, multiply, add those up. So that's out. Good, perfect. So now I'm going to take out the -5 over 2. Don't let it scare you that it's a fraction because first thing you got to multiply it by is a 2, and then the 2's cancel, and you're just left with -5. Those add up to 0. 0 times anything is 0. Then we have a 2 again, which we know those 2's cancel, and we get the -5. And then, of course, our remainder is 0 again. So now we're left with 2x squared plus 0x, which I'm not going to bother to write, plus 2 equals 0. And this is what we need to solve to find those remaining 2 solutions, which we can tell are imaginary. So in order to solve this, I'm just going to try to get my x squared by itself. So I have 2x squared equals -2. Divide both sides. I have x squared equals -1. And of course, when I square root both of those, I get positive or negative, and the square root of 1 is simply just I. So my remaining 2 solutions here are positive I and negative I. All right. So hopefully you understand how to find those possible rational zeros and also use them to divide out and find any remaining zeros that you need to find, even if they're imaginary. Okay, solving a multi-step problem. So this can be used a lot to find a missing dimension when we have volume or different geometric formulas. So for example, this first one here, the given information for us is the length of a desk organizer is 4 inches greater than the width. The height is 1/3 of the width. And then they're giving us the volume. Okay, but then they need us to find all of the dimensions. And the way I figured this out, right, is that I always ask myself, well, which is the one we know nothing about? We know volume is length times width times height in any order, right? So for finding volume, we multiply the 3 dimensions of the figure. So they have it here in height times length times width, but length times width times height, whatever. Now, of those 3, we're given a little bit of information about the height and a little bit about the length, but they're both in relation to the width. And the width, they didn't tell us anything about it. So that's why the width is just going to be the single variable. And in this case, we're using x. So then the length was 4 inches greater than the width, so that's why it's x plus 4. And then the height was 1/3 of the width, so that's why it's 1/3 x. And then, of course, the volume is given to us, and it was 21. So if we were to work this out, then, of course, we're multiplying these 3 things, right? Now, when you multiply things, remember, it doesn't matter what order you multiply them, so whatever looks easiest. So I would probably go ahead and multiply these 2 monomial terms, and I would get 1/3 x squared. And then I would multiply that or distribute it to that remaining expression there, the x plus 4. And I would get 1/3 x cubed plus 4/3 x squared. Now at this point, the suggestion here is to multiply each side by 3. Well, that's because these are these awful fractions. So if I multiply a 3 to the side of my equation here, the fractions will cancel and I'll just be left with this x cubed plus 4x squared. But anytime you multiply one side of your equation, you have to do the same thing on the other side. And 3 times 21 is 63, and that's where that comes from. Now, at this point, anytime you have any type of polynomial equation, you want to get everything on one side of it. So you can either factor it, use quadratic formula, whatever the method is that you're going to use at that point. So we're moving that 63 then over to the other side, which is where we get this piece from. Now at this point it's 0 equals, but remember you can just substitute a y in there, and then you could use your graphing calculator to see if any of these are going to show up, because you need to solve for these x's, and we know there's 3 possible x's that we could get. Now, if we list the possible rational solutions here, they're going to be all those factors of 63, which are plus or minus 1, 3, 7, 9, 21, and 63. So keep this in mind, because if we use our graphing calculator for this, the 1, the 3, the 7, the 9, and those versions there will all show up on that xy axis that we typically have our graphing calculator default to. But if the solution is 21 or 63 or the negative 21 or negative 63, they're not going to show up on that screen. So something to keep in mind. So let's type it in our calculator and hopefully one of them will show up. So if I go to my y equals, I clear it out, and where am I here? X cubed. And then we have plus 4x squared, and then minus 63. Now when I graph it, luckily, one of the zeros shows up and it's that positive 3 there. Now remember, just because we're getting this x equals 3 doesn't mean there couldn't be another x equals at 21, negative 21, 63, or negative 63. We don't really need to find it, though, as long as we have 1, because remember, this is only a cubic polynomial, and if we divide out the 1 that we already know, we can probably factor and get the remaining 2 if they are rational zeros. So I'm just going to do that. Otherwise, I'll have to play around with my calculator. You could go into your table, and then you could, so second graph gets you your table, and then you could scroll up or down these values and look for the x values of 21 or negative 21 or 63 or negative 63 and see if the y values are zeros. the way it is here for the 3. See how it says 3, 0? If you have any other intercepts or zeros, it'll have a 0 in the y column. But it does take a while. You have to keep clicking on your calculator. It's kind of a pain. So instead, I'm just going to divide out my 3 synthetically here. So I had the 1 for 0 because there was no x, and then negative 63. Do the synthetic. We get that remainder of 0 there. So now we can look at this remaining piece. This would be x squared plus 7x plus 21. But if you try to factor it, you'll notice there's no numbers that multiply to 21 that add up to 7. So that tells you the other solutions are imaginary. So we don't need to worry about them because we're doing volume. And the width is going to be this answer, and you can't have an imaginary width of a box. So we don't have to worry about finding those now. So the last thing you would do is just find all your dimensions. So we knew the width was 3 inches. Then the length was 3 plus 4, which would be 7 inches. And the height is 1/3 of 3, which would be 1 inch. Okay, on the last page, so we're going to do a pyramid problem. Now, I'm just going to try to do a rough sketch here because I think sometimes it helps when we have a visual. And I'm not the best artist, but hopefully you'll get the idea. Okay, so this is my pyramid. That black line there is my height. Okay, now this pyramid says it has a square base. So this and this are each going to be length of x, right? And then it has a height of x minus 2. And that's the height from the center of the base straight up to the tippy top. And the volume's 3. Now the volume for a pyramid is the area of the base, so the area of this entire bottom, which is your length times width, times 1/3 of the height. So sometimes you can see it written this way, or sometimes people will write BH over 3. It's basically the same either way. Now, since I already know that my volume is 3, I'm going to put that in. My base, my area of my base will be x times x, which is x squared. My height is x minus 2. And then I have my 3, which is here on the bottom. Now, at this point, if I want to solve this, right, or get it all by itself, that's pretty easy because the 3's are just going to cancel. You want to look at it that way. And then this is what you're left with. Or if you multiplied both sides by 3, the 3 on the right would cancel. You'd have a 9 over there, but we'll do this. So you multiplied this whole thing by 3, so it's cancel. This whole thing gets multiplied by 3, right? So we'll do it that way, make it similar to the other one. So now I have 9 equals x cubed minus 2x squared. And I'm going to bring that 9 over. It becomes minus 9. And now this is what's going to go in your calculator, right? So if you go into your calculator, y equals, and we have x cubed minus 2x squared minus 9. And you graph it. And we do see that we have one x-intercept there of 3. Because we see this little curve down here, I'm going to guess that the other two are imaginary. So we have x equals 3. Because the other two are imaginary, we don't need to worry about them because we're dealing with a physical object that has dimensions. You can't have imaginary values there. So then that would mean that x, which is the length, is equal to 3 inches, right? And then this x minus 2, this height here, is equal to 1 inch. Or unit. I don't know if it specifically said inches, but okay. And then finally, we're going to do a prism with the volume, similar to the first problem. This time it's telling you there's 3 lengths, x, 1/2 x, and x minus 1. And the volume is 24. So again, we know volume equals those 3 dimensions just multiplied together. So we have 24 equals And then you can multiply these together in any order that you'd like. Length times width times height. So I have 24 equals 1/2 x squared times x minus 1. Then I'm going to distribute that. So I will have 1/2 x cubed minus 1/2 x squared. And I'm going to move, you can move the 24 over now, or if you want to get rid of the fractions first and then move it over, it's really up to you. We end up with 48 equals, and now our fractions cancel. So we have x cubed minus x squared. And then we're just going to move that 48 over to make this a polynomial that's basically equal to 0 or y, so that we can now type it in our graphing calculator and solve. So putting that in, we have x to the third power minus x squared minus 48. Now keep in mind 48, all of the factors of 48 would be possible solutions here, and we're just getting this 4 to show up on the calculator. So we know x equals 4. Even though there's 2 more possible answers, I could just synthetically divide out the 4 so that I don't have to worry about looking for them on the graph. 1 times 4, add those up, 12, and then that gives me 0. This is x squared plus 3x plus 12, but it's not factorable because there's no two numbers that multiply to 12 that add up to 3, so I know my other answers are imaginary. So now I can just go ahead and find my 3 dimensions. So the first one would obviously be 4 for that x. Half of 4 is 2, so that would be the second dimension, and then the third one, 4 minus 1, would be 3. So 4 by 2 by 3.